because the sign bit is right here. So 7F is minus 1 in 7.20 format. And if you just read this number to a 32-bit parallel port, you get, and then shift it right by 20 bits, you get 127, because that's what 7F is. So there's various solutions, some of which are really contorted, which I thought up on Friday and then somebody else got right. And that is, slurp this bit string into C, and then shift it left 5, and then divide by 2 to the 25th. And when you do that, if you have all of the typing correct, it does the right thing and makes a sign extension. It's a much easier way to do it, which I thought of as I was driving home on yesterday, of course, after I stopped talking to people. And that is, it's really easy to bit extend a string in Verilog. It's like a concatenation. A concatenation operator will add 5 bits to the front of the word. So you take the 7.20 format and you add 5 more bits to the front of it, and now you have 32 bits. And if these 5 bits match the high order bit, you've just done the sign extension in hardware.
Isn't it easier to use a 1220 on Linux side completely and then extract MSB alone on?
What should I say again?
You use a 1220 format on the C side.
A 1220 format?
Yeah.
You can do that, but remember that but the FPGA is still only going to generate 7.20.
Yeah, I can do an interface in the Verilog that just takes the bits. It's easier.
Yeah, well, I mean, that's right. That's what I'm saying. Just add 5 bits to the front of this thing with a concatenation statement. Before you write it to the I/O port, concatenate 5 bits on the front that match the sign bit. Done. Much cleaner, much easier to handle than trying to debug the C typing. Any other questions on Lab 1?
Can you talk a little bit about why the HPS, well, what we tried to do at the beginning was have it asynchronously try to read data from the FPGA solver, and it was reading every 700 something points.
Right, because if you, how fast are you running the solver? CL clock 50 or clock 100?
I think we divided the clock by.
Tell me you didn't divide the clock.
What?
Don't ever do your own clock divider, because that will almost guarantee that the design does not meet timing.
Okay.
If you decide you need a new clock, use a phase lock loop, which is a piece of hardware on the chip, which will generate phase locked clock pulses. The main reason for this is that if you generate a clock divider and then take a bit out of the clock divider register and use that as your clock, then you have just used random logic connection to drive a clock line. And the delta T between the logic and the main clock is not well defined. If you use a phase lock loop, then the clock signals come out over an isochronous network on the FPGA that is much more likely to deliver clock pulses synchronously across the chip. Don't use clock dividers. Now, if you're running a 50 kilohertz clock, it hardly matters, right? Because the logic is so much faster than the clock, it will make the deadlines. But to my way of thinking, the easiest possible way to synchronize these two is have the HPS through an I/O port, through a parallel I/O port, do that. The solver runs on the updates the variables on the leading edge. The HPS drops the variable, the clock pulse back down, and then reads x1, x2, x3, raises the clock again. Yeah.
So we did get that working, in fact. But my question was, why is it that slow? Isn't like the ARM at like a gigahertz or something? Is it because of the VGA stuff?
Oh, why does it take that many cycles?
Yeah.
So, I've said a couple of times, but it doesn't stick until you see a real example of this. The heavyweight bus only does 7 million transactions a second. The HPS is running at a gigahertz. Do the division. 143 cycles per bus transaction. I keep a table of reciprocals in my head. So I happen to know that the reciprocal of 7 is 0.143. That's why it takes so long. The bus is quite slow compared to everything else. Any other questions about Lab 1?
I'd like to back up to this part, 720. Do you mean we change all the 5 bits at the end to the same bit as sign?
Yes. Yes, so if sign extension means that you have to, that all of the bits that are not significant to the left have to match the sign bit. What else? Did that answer what you were asking?
But we can also move that 1 bit aside, right? Like have one more variable and write 1 bit aside zeros and then the 26 bits.
If you add zeros, it forces it to always be positive. You can't move 1 bit. 2's complement has all high order bits set that are not being used. It is not sign magnitude. A whole bunch of people apparently don't know the difference between 2's complement and sign magnitude, because I've seen a bunch of people make that particular mistake. We'll set the high bit and it'll be negative. That's sign magnitude. The arithmetic doesn't work that way in the FPGA. What else on the Lab 1? Start talking about Lab 2. Because a week from today, it starts. And there's a fair amount to talk about. There's the wave equation, which probably you haven't thought about extensively in a long time. And have any of you ever done a numerical solution of the wave equation? No. Okay. Yes? No? No. So, it's the first thing I programmed up as soon as I got assembly language running on my Mac 1. So, what we really need to do here, this is going to devolve into a bunch of steps. One is to derive the finite difference version of the wave equation, figure out what the boundary condition should be for a drum, because every PDE has to have initial conditions and boundary conditions, right? We have to make sure we have courant, C-O-U-R-A-N-T, stability. Then we have to worry about numerical accuracy, number of places. number of bits, and a few other things. Then we're going to need to talk about parallelization, because a single processor on the FPGA will not be fast enough to solve this. And in fact, the HPS will not be fast enough to solve this. So we're going to have to build a parallel processor array on the FPGA to solve the wave equation in real time being 48 kilohertz audio update rate. Because we're going to put out audio, so you're going to press the button. I think I've played this before, right? Yeah, I've played those examples before. You're going to press the button, it's going to go boom. So we have to talk about the audio codec, which is a separate piece of hardware from the FPGA, but which communicates with the FPGA. It has a command language that has been mostly abstracted away by a piece of IP from Intel Altera, but you still need to know a little bit about how it works and how that abstracted interface works. It looks like a FIFO, audio FIFO. Then we have to talk about how to write a bus master for the QSys bus, because I'm going to give you the design choice of either having the solver run on the FPGA, read back to the HPS, and then the HPS runs the audio interface, or going directly from the solver through a busmaster and Verilog to the audio codec. One is easier in some ways, the other is easier in other ways. The busmaster is slightly more logically clean. The HPS, you at least know how to program. In any case, you're going to have to write a busmaster for Lab 3, because Lab 3 won't work without a specific busmaster, because the bus is too slow for Lab 3. For Lab 2, it's fast enough because you're asking for 48 kilosamples per second from the solver to the HPS, and then from the HPS back to the audio codec. So that's only 100,000 transactions a second, well within the 7 million that we know it'll produce. So it's possible to use the HPS for Lab 2, but not for Lab 3. So you might want to do a busmaster, you might not. Depends on your personality and a bunch of other things. We'll talk about all these. Any questions on the overall layout? This is kind of like the order in which we're going to do things for the next, like, 6 lectures or so. A couple of weeks worth. So if we go to Lab 2, I'm going to ask you to simulate the motion of a square drum head. Think of it as a plate, a suspended membrane. So, in which each element each mass element of the membrane can move up and down. So this is a square, and a point in the square is moving up and down. The points are coupled throughout the membrane by an elastic force, as if it is a stretched membrane. And so you get waves propagating on this structure according to the linear wave equation. Of course, the grid has to be fine enough to support the level of detail that you want to calculate. And of course, you have to solve it fast enough that you can get something meaningful out of it, in this case, sound. So the goal is going to be to build a simulated drum of at least 40 by 40 grid, so 1600 grid points, running at 48 kilohertz. And a general, sort of a hasty calculation would suggest that this is going to require something like 1 billion multiplies a second. Maybe a little more. So it's not a huge computational load by modern standards, but it's pretty fast. And so we're gonna need to figure out how to take the continuous wave equation and put it onto this grid in a self-consistent fashion, so that it's quantized in space and in time. So it's going to be quantized in X, it's going to be quantized in Y, and it's going to be quantized in T. We have to figure out what the boundary conditions, what are the boundary conditions of a drum? What happens at the edges of the drum? They move up and down?
Stationary?
Hmm?
Is it stationary?
They're stationary. So the boundary conditions you're probably going to choose are that the displacement equals 0 on the boundary. Now, when did you do partial differential equations? Is that like Math 3? Remember the difference between a von Neumann boundary condition and a, oh my gosh, what's the other one called? But there's two typical boundary conditions. This one is, we're going to use is u equals 0, although you could make a free boundary and then it sounds more like a struck plate. So the boundary conditions are going to be 0, like any wave equation in a second order system, because it's F equals ma, it's a dressed up version of F equals ma. And so you know that you're going to have two initial conditions for each grid point. A mass, a position, and a velocity, just like you would with any spring mass system. So there's going to be two initial conditions across the whole grid. And what I'm going to suggest is that you use a position function across the grid that is more or less Gaussian, a Gauss of rotation, so that it's centered in this axis and in this axis. So it's going to be a Gaussian of rotation on the grid with v equals 0. So it's going to be like you took the membrane and went whoop, and then let it go. So the initial condition for u is going to be something like this, and for du dt is going to be 0. Probably. Courant stability. We're going to talk more about this, but the basic idea is that you better not have the wave propagate faster than about a half a grid point per time step, or you'll get aliasing. If it's propagating too fast, you're losing information about the history. And so there is a maximum speed of sound, so to speak, on the grid, which we're going to abstract out into some dimensionless thing I'll talk about. But there's going to be a Courant stability criterion which limits how high a pitch you can get off the drum. If you get near that boundary condition, if you get near that stability limit, and your arithmetic isn't too good, then the system will oscillate anyway, and the resulting sound will wake up the TAs. To this broadband screeching. that's the arithmetic so far. I'm going to talk about strategies for parallelizing the code, but that'll be a couple of lectures from now. There are some really good articles on finite difference solution of wave equation. I'm going to talk about this first one in some detail, but if you want to read ahead, strongly recommended. Really what you're going to be doing is simulating equation 218 in this paper, which is a recurrence relation. It's a recurrence relation, which means that if you know all of the values for time t, then you can step ahead one step to t plus 1. In other words, you can advance the solution one time step, which is what you're going to do. Then you record all those values and do it again. One thing I'm going to ask you to do after you've simulated the drum, a couple of weeks from now, is to export the sound to MATLAB and plot the power spectrum of the sound. The power spectrum for a square drum is analytically solvable. Do you remember from some place or another that the wave equation is analytically solvable on a square domain? Maybe. You can do separation of variables, fit signs in both directions, and get a solution. There's a uniqueness theorem that says if you found a solution, it must be the solution. So the red lines here represent the analytical solution, normalized to the fundamental. And if you normalize the analytical solution to the fundamental of your simulated drum, then all of the rest of the peaks of the simulated drum should fall on the red lines. Well, yes and no. All right, so it seems to work pretty well up to about here, and then that peak misses, and that peak misses a little bit. That was not bad, the rest of them were just completely meaningless. So up to about 1, 2, 3, 4, 5, 6, 7, 8, ninth harmonic, it was not bad. But above that, it wasn't working very well. Now, that may not matter too much because this main peak is at minus 35 dBs, and this peak is down at minus 65, so it's 30 dBs quieter. You don't really hear it very much. But more or less, the bigger the drum and the finer the time step, the better match you'll get between these calculated analytical results and the simulated drum. So I'm going to ask you to characterize that in MATLAB towards the end of this lab. There's some papers on parallel implementation of finite difference schemes, which you may want to read. There's a article on we're going to go through on the Wolfson Codec, but not today. It's kind of cute. It's really a high-speed DSP device that happens to live on a very tiny package. But what I'm going to ask you to do is to start by simulating one node. So you're going to simulate a one-node drum. So the connections on the drum, the boundary conditions are going to be 0. the only point we're going to look at is the motion of this point. Now, if we look at it from above, then we have this point going up and down. And what would you guess the motion would be? If you just had to guess, it's a mass and 4 springs. What would you guess the motion is? Say again? Under damped sinusoid, and you'd be exactly right. So, so you can simulate this in Model Sim and look at the output and say, oh, that's reasonable, that's unreasonable. It's continuous, it's decaying, it's exponentially decaying. The frequency you could calculate if you wanted to bother to do that based upon the speed of sound or the stiffness of the springs and the sample rate. But basically, you're going to want to simulate one node, simulate your solver for one node until you get a damped sine wave. Then you could, for instance, hook 2 or 3 or 4 or 5 of these together. Just take it, stamp, 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 hook them together near as neighbors, and make a bigger drum. Which, by the way, this is one way of making a parallel system, would be to make a solver that does one node and just make a 1,600 stamps of it. In this case, it doesn't work because there's not enough multipliers on the chip. There's only 174 multipliers. And I'm going to force you to make a nonlinear extension of the wave equation because you know what pitch glide is on a real drum? You know what pitch glide sounds like? If you hit a drum really hard, and the drum is fairly stiff, like a bongo, then you'll hear a higher pitch that becomes lower as the amplitude drops. It goes boom. And the reason for that is that you hit the thing really hard, you stretch the membrane. You stretch the membrane, the speed of sound goes up, and the pitch goes up. And as the amplitude drops, the stretch becomes less and the pitch goes down. And so the pitch glide can be a few percent on real drums. So it's quite noticeably, acoustically noticeable. And I want you to be able to simulate that. I would start out with a row around 1/16, because if you run row up near to the limit of 0.5 with one node, you're going to be at the border of aliasing, and the border of aliasing for one node looks like a square wave. And you're going to say, all I got out was a high frequency square wave. When you see that, drop row a factor of 5 or 10 and try again. And I'm going to suggest that you use 1.17 fixed point. Why? Well, it turns out that the native size 1.17, the native size of the multiplier on this FPGA is 18 bits. Fits. Furthermore, the audio codec is 16 bits. Aha! Oh, by the way, it's 16-bit 2's complement. So it fits the arithmetic system perfectly. No conversions necessary. 16-bit 2's complement. And I did a bunch of simulations in MATLAB. And by the time I got to 17 bits, I could just not quite tell the difference between infinite precision or IEEE precision and fixed point precision. So it was good enough. not wonderful, it's good enough. You could do better if you went to 27-bit. You went to 1.26 format, you could do better. Then you have half as many multipliers, so you have to even have better parallelism. And we'll see why that is in a little while. The next step for the Verilog would probably get a generate statement working. Generate is a construct in Verilog in which you write Verilog that generates Verilog. Oh, just kill me. Why not do it in Python? And some of you will. I prefer to do it in MATLAB because I'm a masochist. And I've used MATLAB for 30 years, so I'm used to it. But you're going to write a Verilog loop which generates nodes. And what it does is to generate Verilog that generates a fixed set of nodes. It's not iterative, but rather it's a way of generating hardware that is repetitive in space. So you want to get to generate and emulate, simulate. Emulate, I don't think is a word, but it might mean to burn. No, you want to simulate the nonlinear PDE solver, and that's a typo. That should say 40 by 40 now. I just changed that today. And I changed it, I made the lab a little easier by saying there are no extra points for making a gigantic drum. Last year I gave extra points for gigantic drums. The biggest drum generated was 80,000 nodes, which is fantastic, it's amazing. I'll show you how they did it, but I don't expect that. For HPS testing, I wrote the system for the HPS. I wrote a drum simulator for the HPS, and with a nonlinear term, the best I could do was about a 25 by 25 grid. It sounds pretty good. Let's see if we can listen to that. Hear the pitch glide? You hear a little bit of high pitch whine on it? That's aliasing. There's not too much, but there's some. So this audio code works up to about 25 by 25. That's why I'm asking for a 40 by 40 on the FPGA, because it's big enough to be interesting compared to the HPS. And then I'm going to ask you to characterize how the HPS solution varies with, solve rate varies with grid size. How would you guess it varies? Probably with the square of the grid size, right? So week 1, next week. Simulate a 10 by 10 or greater linear grid to produce a sound by exporting the wave to MATLAB. So you're going to show me the waveform in ModelSim and also export the sound and listen to it using SoundSC function in MATLAB, yes.
This is the week after next.
No, next week.
Wait, but we still have week 3 of Act 1.
Oh, I'm sorry, yes, you're quite right. It starts next week. It's the week after next week. Yeah, I saw people go, oh crap. No, you're quite right. I'm leaping ahead a week. Great leap forward. And I want you to, at the same time, I want you to show from Verilog, from the simulation, how many cycles it actually took to solve the audio cycle. That's going to give you an idea of how to parallelize. And at the same time, since there's usually 2 or 3 of you in the group, I want you to modify the HPS program. I'm giving you the linear version. I want you to produce the nonlinear version. That means some recoding, because the linear version will do a 30 by 30 drum using all kinds of nasty shift tricks rather than doing fixed point multiplies. I want you to modify the code to use fixed point multiplies. Week 2 then will be to simulate the nonlinear solver on a 24 by 24 grid or greater using only 174 multipliers, because that's what's available on the chip. So you're going to have to figure out how to multiplex the multipliers. And to demo the code you debugged the week before actually running on the FPGA. So show the audio codec running on the FPGA to make a sound. And then, of course, the last week is the full system, which is the at least 40 by 40, no greater than a 4:1 aspect ratio. I put that in because one clever student gave me a 1600 long by 1 drum, which is a string, which had a natural frequency of about 0.0001 hertz. You couldn't like hear it. You could watch it on the LEDs. But so 4:1 aspect ratio. That means the X and Y direction have to be within a factor of 4 of each other. And you don't get to use symmetry to expand your calculated grid size. So no tricks like symmetric drive. If you hit the system in the center, it's got 2 axes of symmetry. You could simulate 1/4 of the drum, as long as you were careful with the boundary conditions. That doesn't count now. Can't do that. Minimum of 3 buttons should produce different timbres. It can be set by boundary condition. Eta rho. Eta is going to be the damping coefficient. Rho is the speed of sound, in other words, the pitch. And tension modulation is the nonlinearity. And at least one timbre must include audible nonlinear tension effects. And the solver has to be phase locked to the audio codec. So the nice thing about the audio codec is it gives you status information in a user interface that tells you when space is available in the FIFO. If space is available, you load the FIFO. If space is not available, you stall the solver. Easy to synchronize. You can use any kind of parallelism you want. It could be fine-grained parallelism, in which you have little tiny processors, you have a whole ton of them, or it can be a coarse-grained multiprocessor, in which each of the processors is fairly heavy duty, as long as they're fast. And I am going to ask you to Prove means display on the oscilloscope. That's proof. Display on the oscilloscope that it takes less than 20.8 microseconds to do each sample. 20.8? Oh, it's 1/48 kilohertz. And then lastly, record the audio output back to MATLAB to show that your simulation matches the drum modes, the spectrum matches. So, any questions about that? There's kind of a lot of stuff to plow through. It's not so bad. The wave equation, like all partial differential equations, when turned into a finite difference equation, becomes a set of algebraic equations. And so what you're going to do is to solve the algebraic equations as fast as possible. We'll talk about that next time. I'm not going to talk about that today. It takes a few minutes to talk about. Is anybody sad that there's not going to be extra points added for bigger drums? Yes? You're sad?
Yeah.
Okay. You don't look sad. At least you're smiling quite a bit there. Let me just show you equation. Let's see if I can find 2.18 here. Just to show you. I mean, there's lots of stability stuff in here, but there it is. This is the one-dimensional discretization, which we don't care about, although it's of some interest if you want to make a string simulator. But this is the two-dimensional recursion equation. And I'm going to talk about this in detail next time, but just to sort of get the feel for it, there's the value of u at the next time step is gotten by the sum of the four neighbors minus the position of the node of interest. So the sum of the four nearest neighbors. That says that in some sense, the value of a node is the average, on the next time step, is the average of the four nodes around it. And if this was a stationary system, if dt was 0, if there was no change here, that would be exactly Laplace's equation. But there's another term here. So this is these represent these stretches of four springs, right? From I plus 1 to I minus 1 to I, j plus 1 to j, and j minus 1 to j. So this represents the forces in four different directions from four different elastic connections to other points in the node, in the drum. This term represents friction. It's the amount of energy lost during one cycle, which is going to be low. We're going to, for real drums, the Q is high, the losses are low. We're going to set the friction to something like 0.001 normalized units, 0.01 of the energy or so. And then there's a drive term down here, but you're not going to drive the drum, you're going to strike it. And so there's not going to be any functional drive after t equals 0. So all of the drive will be folded into the initial conditions. So let's see, how many operations? 1, 2, 3, 4, 5. Adds, it turns out the numerical stability is a little bit better if you do the subtractions first. So that's going to be 5, let's call it 5 adds. Then a multiply by row. That has to be a real multiply. It has to be a real multiply, not a shift and add kind of thing. Then there's going to be, so that's 5, that's 6. Then there's another add here and a reciprocal? Oh no, say it ain't true. What do? What is the first thing that comes into your mind when you see a 1 followed by a small number? 8 is the damping is small. When you see 1 followed by a small number to the -1 power, what words come into your mind instantly? Taylor expansion. And what's in my mind? So whenever you see that, we're gonna eliminate that reciprocal with the Taylor expansion. Also this one. No, we don't need it. No, this one, but not this one. This one's not reciprocated. So there's going to be about 10 arithmetic operations per node per time step. Times 1,600 nodes times 48,000 times a second. So you multiply it out. It's a lot of multiplies. Any questions on this? I'm going to go into all this in much more detail. This is just the kind of warm-up lecture to give you something to read over the weekend. Yeah. Next weekend, not this weekend, though. Are there any lingering questions on Lab 1? Lab 1 write-up is due 1 week after it's demoed. Is it the same guy every day? Slow learner. Okay, let's go to the lab. Do some check-offs.